Alright, hey, let's talk about actual PIC chips, because we've been working with the simulator. That's a change that happened when COVID hit and we moved all our labs to be remote, and we haven't gotten back to in-lab labs yet. But if we were doing our labs in the actual laboratory, in the collaboratorium, we would be working with physical chips and using them to control, LEDs, motors, things like that. I think we're going to take a class towards the end and just play around with some actual physical hardware. And I've been figuring out some tools that will help us do that. And so I just want to kind of do a quick demo of how interacting with an actual chip works. So we need a programmer. We use the PIC18F1220. There's a bunch of these available in the collaboratorium, and they have 6 outputs. We use 5 of these. They hook up through a USB cable to your computer, and we connect them to the PIC chip through 5 lines. So we put power 5 volts on pin 14. We put ground on pin 5. The clear / programming pin is pin 4, and then there's a clock and a data, so we send out data in serial. There's a signal line that carries the actual data, and then there's a clocking line. So the programming data line, PGD, is right here on pin 13, and then programming clock is on pin 12. And the way we hook it up to the PIC kit, this is for a PIC18F1220, but it's the same pin out. Pin 1 goes to pin 4. Pin 2 is 5 volts to 14, pin 3 is ground to 5, and then pins 4 and 5 go to 13 and 12. So I have borrowed a PIC kit 3 and have hooked that up to, this is an actual PIC18F1220. It's just, the little 18-pin chip that you see in the data sheet. And pin 1 is over here on the left, so this first line coming out of the programmer is this white line here, and that goes over to pin 4, which is the master clear. Yeah, pin 1's over here on the upper right. So there's pin 4. That's the main clear pin, and then the next line, blue, that goes to power over here, and then the next line goes to ground on the other side, so that's pin 5, and then those last two, the clock and data, go over to these 2 lines over here. The main clear line, which is pin 4, also gets pulled up through this 10K resistor to 5 volts. And so when the system wants to program the chip, it'll pull that line down, but we keep it pulled up high normally to keep the system running and out of the reset state. So what I've done is I've configured a single LED here, and I'm coming out of pin 1 on our PIC chip. So pin 1's going into the LED. The other end of the LED goes through a small resistor and goes into ground. So anytime I assert pin 1 to be high, the LED should turn on. So let's go ahead and look at some sample code. And I just made a really simple blink program. So we configure it the normal way. Watchdog timer is off, low voltage programming is off. We include our file. I've got our standard delay loop that we used in lab 3, so a pair of nested loops. 7F into ADCON 1 as always, and then I just clear bit 0 of tris A. So bit 0 is a 0, that means it's an output pin, so I can write to RA0, and RA0 is pin 1 on the chip. So my main program, I call my delay, and then I say bit toggle, port A, bit 0, and go back to loop. And the delay code, you've seen this before, so the inner loop waits for 1/10 of a second. It decrements this file register D1. If it's not 0, it goes back. Sorry, the 10th loop is down here. Decrement D2. If it's not 0, go back. So this runs 256 times, 3 cycles per iteration. It's about 800 cycles, 1/10 of a second. And then the main delay code, I put, let's go ahead and put a 5 into W. And then we'll put that into D1, and then our main delay loop we wait a tenth of a second, we decrement D1. If it's not 0, we go back, wait a tenth of a second, decrement D1. So since D1 is being set to 5, this will call 1/10 5 times. It's a half-second delay. Nothing too exciting going on there. So we assemble it, and that builds it. And I've introduced a new command. This won't work on the Linux server, but we'll find a way to run it in class. Pick program, and we just pick program blank.hex. Instead of debugging it, we use this pprogram command. And let me move this out of the way so we can watch the action. So it'll go ahead and we'll find the programmer. It lights up these LEDs to indicate that it's active and it's doing different things. And it will read the hex file for our blank program. It'll erase what's currently in the PIC chip, checks the erase, that was successful, and then it will go ahead and load in our new program. It said operation succeeded, and now you can see we've got our LED blinking, on for half a second, off for half a second. And if I wanted to do something different, like if I wanted to be on for 1.5 seconds and off for 1.5, I could load a 15 decimal into there, reassemble it, reprogram it, and now it should stay on for 1.5 seconds and then go off for 1.5. So it's still running the old program. Now it's erasing. Now it's going to load in the new program. And it succeeded, so it's off. Then it goes on. Then it goes off. And it's about a 3-second period. 1.5 high, 1.5 low. So once you've got this dialed in, once you've got this hooked up, and you've got the tool chains, very rapid prototyping, right? To make that change. Only took me about 10 seconds, and then it took the tool a while to actually reprogram the device. But it's very quick turnaround when you have a change and you want to put it into the PIC chip and try it. Lets you go through lots of iterations very quickly. So like I said, I think we're going to take one class, and I'm going to at least get this set up on one laptop in the classroom, and let people load code in if they want. We can hook up different things to the output and so on and see what it does. But I'm going to see if I can also get this to work under Windows in a way that would let students do this also from their own laptops. So that's a plan in progress. But anyway, I've been trying to get this to work off and on for a few weeks, and I finally got it to work, so thought I would just share that out. All right, see you next time.